You might be wondering, what is a commit in Git? I have described a commit as a snapshot of the project files at a moment in time, but let's take a look at what that really means. Let's imagine that you have a project with two files, A and B. Let's imagine that when you first tell Git to start tracking this project, those files have some contents. It doesn't really matter exactly what those contents are, so I'm just going to refer to the contents as A1 and B1 respectively. We can tell Git to commit those files. This will be our first commit. Very exciting. Every commit has to have a short message that should describe the changes that were made. Here that message is just going to be initial commit. Git creates a sequence of letters and numbers to identify this first commit. This is called a hash, and for this commit the hash begins E5X91N. While this sounds like a great name for a Star Wars droid, the hash actually contains 40 characters in total. I'm just giving you the first 6 for the sake of simplicity. What do we do now? Well, in all likelihood, you make some more changes. In this case, maybe you edit file B. The contents of file B are now different. They are no longer the B1 contents, so I'm going to refer to these new contents as B2. Maybe you changed one line, maybe you changed 100. It doesn't really matter. What does matter is that you decide that this is a good point to create another checkpoint in your project's history, to take another snapshot of the state of the files, to make a second commit. So you make commit number 2, except that it's not called commit 2, it's called commit 4OLS8G, etc., etc., which is the hash for this second commit. Remember that every commit gets its own hash. And what does commit 4OLS8G take a snapshot of? Well, file B is in an updated state B2, so, assuming that we staged the file to be added to the commit, this new commit will make a copy of B2 and save that copy in the .git repository folder. But file A has not changed. It's still in state A1, and this second commit records that fact. Remember that we also need to write a commit message, and that message should briefly summarize the changes that are recorded in that commit. Here we write a message, edit file B. Let's look at one more example. Let's say we edit and save both files. Now we have new versions of both files, A2 and B3, and we can stage both of these new versions to be committed in the next commit. When we do that, we get a third commit, which is identified by yet another hash, the first characters of which are FD8EW3, and it has a message, more edits. As an aside, this is not a great commit message, as it doesn't really describe what was changed. If at some point in the future you wanted to remember what history this commit was recording, you would have to go into this commit and compare version B3 to version B2, and version A2 to version A1. A better commit message might say something like, added histogram to file A and summary statistics to file B. Future historians of your project, and that's likely to be you, will thank you. So there we have it. A commit takes a snapshot of the project's files, gives them an identifying hash, and adds the commit to this sequence of commits. This is one of the key ideas behind the Git version control system. But this brief overview might have left you with some questions. For example, what exactly is a hash? A hash is the output of a type of function called a hash function. Remember functions? Those things that take in some data and give you some other data back out? This is the same concept. What is special about a hash function is that it can take in a piece of data of any length, and it will return a piece of data of a defined fixed length. For example, we can use the git hash function to calculate the hash of my name, which is 45EE08, etc., etc., In total, there are 40 characters in this hash. And you could feed any piece of data into this hash function, a single letter or the entire text of Moby Dick, and you would still get a single 40-character hash back out. But here's an interesting thing. If I change a single letter in my input data, the hash will be wildly different. Here is my name hashed again, but with a single typo. And sure enough, the hash is completely different. Now hang on a second. A hash takes input data. We've just talked about that. So what input data does Git supply when it is creating the hash identifier for a new commit? I'm glad you asked. That's a great question. Git hashes a whole bunch of stuff. In fact, pretty much everything about the commit gets fed into the hash function. All the things in the boxes on this slide get hashed. The commit message is fed into the hash. The name of the author, that's you, gets hashed, as does your email. Cast your mind back to the start of the semester. I know, it was a long time ago. But do you remember typing 2 lines into the terminal in RStudio to tell Git your name and email address? These get attached to the commit as metadata, so that future historians know who to blame for a particular commit. But they also get included into the commit's hash. We also hash the time the commit was made, the version of the files that the commit is snapshotting at that time, and then we hash the hash of the previous commit. Yes, you heard that right. We hash the hash. It's hashes all the way down. A lot of things went into that hash function, so let's take a look at it again with an example. Do you remember our initial commit from the start of this video? In that slide from a long time ago in a galaxy far, far away, we had a little green Star Wars droid of a commit called E5X91N, which captured the project's files in their initial A1 and B1 states. How did Git turn all of this input data into the hash E5X91N? All the data about the commit, everything on the left of this picture, gets stuck together into one big input and fed into the hash function, which is represented by the big downwards arrow on the right. What is the stuff that goes into this big lump of input? Well, first, all the metadata that we just talked about, the commit message, the commit author and their email, and the time and date. We also stick on the project files, but we don't feed the file contents in directly. Instead, we take the hash of each file separately. First, we save a copy of the file in the .git repository folder with a file name equal to its hash so that we can easily retrieve it later. Then we hash those file hashes, and we feed that hash of all the file hashes, we feed that hash into our hash function on the right. So in this example, the hash of all the file hashes is 40 characters beginning with 0OJZWQ. And those 40 characters get fed into our final hash function. I've also left the previous commit on the slide, even though this is the first commit, so there is no previous commit in the project history. So we don't need this for now, but remember it because we'll be coming back to it in a couple of slides. But all those other pieces of information, all of those are stuck together and fed into the hash function, and we get back a 40-character long hash beginning with E5X91N, which identifies this first commit. And we repeat this process for every commit. Here was the sequence of 3 commits that we built up at the start of the video. Each commit makes changes to the project, adding to this chain of commits. But let's think about those same commits as a bunch of data that is getting hashed. Each one contains a bunch of metadata, as well as the hash of all the file hashes. Now here is something interesting. For every commit after that first one, we also include the previous commit's hash, as you see in this picture. So the second commit hashes the metadata and the file hash, as well as the previous commit's hash, E5X91N. Did you think I was joking when I said it was hashes all the way down? But here's the amazing thing. We're building up this chain of commits. Each commit is turned into a hash, and its hash depends on the previous commit's hash. Now, why is this amazing? Haven't I been repeating myself for at least 4 slides at this point? Well, do you remember what happened when we misspelled my name by a single letter? We got a completely different hash. So if we were to change even the smallest piece of data about an earlier commit, the hashes of that commit and every subsequent commit would have to change. We would get a completely different history of hashes. This is what's so amazing. This Git history is now fixed. Another way of saying that is to say that it's immutable. That's a nice property to have when you're working with a group of people. You probably don't want to allow anyone to rewrite history, and this way of tracking changes prevents that. Wow, we've really covered a lot in this video, and I hope you're starting to gain an appreciation for Git. If it doesn't quite make sense yet, then take an opportunity to rewatch the video until it does. The stuff we've learnt here is really crucial to understanding Git. And there are 2 main things that I want you to take away from this video. First, remember that a commit is about taking a snapshot of the project at a moment in time. Second, remember that each commit points back to its previous commit, and so we are able to build up a chain of commits, these snapshots, which allow us to record all the changes that have been made to a project.